So you can see my screen, right?
Yes, yes.
Yeah, okay, good. So hello everyone, and today it's the Quantum Day, so happy Quantum Day for everyone. I'm very glad to participate in this workshop. So and to be good opportunity for me to show you some opportunities to use some real hybrid solver to use to use it like in real world applications. So basically, my presentation is about quantum optimization for solving Ising problems, but in industrial perspective. And because we are late around like 10 or 15 minutes, so I will skip the theoretical stuff and focus more about practical because I don't think people usually like in MENA region has like more information about how quantum work in industry. Okay, so I will start. So in this presentation, I will talk about a quantum annealing method. So uh, I will first of all I will talk about types of quantum computing. So we have quantum gate based and we have quantum annealing. But the quantum annealing, many companies don't consider it as a quantum computer. And it's actually, like even like real quantum computer, it's not like computer, like because the quantum computer can be used for some tasks. So it can be considered more as like tool or something like that. So considering like quantum annealer as is not computer is not a big problem because quantum computer itself is not computer because you can't use quantum computer for playing a game, something like that. So about quantum annealing, this architecture can use just one algorithm, which is quantum annealing. So quantum annealing is like I can say like it's kind of very close to something called thermal annealing, or we call it in computer science simulate annealing. So quantum annealing is the counterpart of simulate annealing, and the key principle of this quantum annealing is utilizing something called quantum tunneling. And quantum annealing relies on something called quantum fluctuations, but simulate annealing depends on thermal fluctuations. So you can see here from this diagram how the difference between quantum annealing and simulate annealing. Like quantum annealing use only quantum properties, but thermal annealing or simulate annealing use just temperature fluctuations. There are something called open system where like you have quantum and temperature, but I will not consider in this presentation. So to just imagine how the difference or where is the advantage of quantum annealing. So you can see here this graph. So this graph represents the landscape of energy for problem. Okay. So basically the classical path, it will go like up and down as you can see here. This is like the initial state. Here's the green circle, and how this thermal jump will happen. So when you are searching and exploring for the solution in this landscape. But in quantum tunneling, you can make a tunnel in this landscape and go faster in the solution. So more diagram to explain how quantum annealing will work. So you can see here in the first diagram, this figure like here energy and here system configuration. And it's not like mathematical it's not like here like system configuration is like variable. No, system configuration, it means here the spins, I mean if you have like four spins, so like here maybe it will be like up down up. So it represents solution. So we built all solution of this system configuration in this x-axis. So it's like, not like function like in math, so it's something different here. So and here the fluctuation of quantum is very big. So what it means, a quantum fluctuation is very big. So all spins or spins in the superposition state. So when it's in superposition state, there is no information, so the solution is trivial. It's the same as thermal annealing. If people know about this simulate annealing algorithm, so how we start, like we make the temperature very high. So when the temperature is very high, if you know like Boltzmann equation, it will make the probability of having energy for each like in this statistical model, it will be the same. So there is no information, so the solution is trivial. After that, we call the system until we get in the minimum configuration of energy. So quantum annealing is in the same design. So, but here we use quantum field equations. So after that, we start making this quantum field equation smaller. So when we are making this quantum annealing, when we make this quantum field equation smaller, so the landscape of the problem will start changing. And when you are changing this landscape of energy, you will get this tunneling. And here, because of this tunneling, you will start having this speed up. And when we make it more smaller and smaller, if you see like the landscape of the problem will be much more complex, the solution will be very hard. I mean, for classical to get into the solution, because we need this quantum tunneling to escape from local minimum. So, so, and the process of quantum annealing is based on Ising model. Why? Because we use something called tensor field for the quantum tunneling. So what's the components of the Hamiltonian? So we have the classical Ising model, which is like a popular model, and here GIG, I will call it like in terms that people right now use it in the quantum algorithms. Okay, so GIG is the couple the energy of the couple between the spins. So yeah, and HI is the energy of the qubit itself. So like if you think about it, so if you have this like system, like 10 qubits, you have between each two qubits, you have this coupling energy, and the I will call it like energy for the qubit. I'm just trying to make it like much simpler. Okay, and we have the quantum fluctuation Hamiltonian, which is minus gamma times the Pauli matrix on x-axis. And as you know, like Pauli matrix on x-axis, it represents the superposition. And here's the gamma. This function, it start like it's like this transfer field that make the quantum fluctuations. So, but before talking about this quantum annealing, we should go about to discuss about the adiabatic quantum evolution. So, there's some mistake that people think that quantum adiabatic computation is a big subset, is a big set. Okay, and they think like quantum annealing is inside the adiabatic quantum computation, but no. Quantum annealing is a bigger set. I mean, adiabatic quantum computation is a subset of this quantum annealing, because you know, like in quantum annealing, we use something called anneals. So it's like it's you know, like you do like 10,000, 15,000 operation to have this probability solution. After that, you make sure like that you get a good solution. So about adiabatic quantum, so quantum system here will evolve via Schrodinger equation, and the evaluation should be adiabatic, so the system should be instance always in the ground state. And we have this condition, which is because like we don't have much time, I will explain the meaning of the equation. So one moment, I want to go to some graph, so make it much easier for us. No. Okay, sorry, but I didn't put more plots, so I will go explaining. So here's this maximization here that you see here. It means the speed of this quantum evolution. So and here's this gamma. It means the gap between two energy states. So what it means? It means that we should make the process of annealing very slow, or we should expand the gap between two energy states, so we can create this adiabatic condition. Why? Because if you make it very fast and the energy gap is small, it will go to excited state of energy, and the solution will be not it will be not optimal. So here we define energy gap. This is delta, as I said, and here this is psi 0, psi 1 is instance ground and first excited states, because like we need the first two states. So we'll use something called Hopf's theorem to, it's related to understand the relation between eigenvalues. So we don't need to go deeper into this. I just will show the condition of the schedule for quantum annealing to make it reach the optimal solution. So here, as we said, we just replace the Hamiltonian with the quantum Hamiltonian that we have before, and we just have gamma in terms of t. So we just need to derive gamma t. So we will get this inequality. So after we get this inequality, we need to bound the matrix elements. So we should find the minimum and maximum element. So because we are I don't want to make a chain of make it take more time. So I will skip explaining all this theoretical and go to the adiabatic condition, because I want to show you many applications about how we can use quantum annealing and really what. So I'm very sorry, but the time is very limited right now. So we should here make this schedule to make sure the system will evolve according to adiabatic condition. So the first demonstration, it was for ferromagnetic Ising model, and this paper, it was by Nishimori, who is considered as the godfather of the quantum annealing, and how he compared between quantum annealing and simulate annealing. He compared with the schedule, because as you saw before, the schedule is the only thing that can make us understand how this annealing process will happen. So the idea is to make schedule, make it the same for both operation for quantum annealing and simultaneous annealing. After that, we compare. So you can see here the probability. Here is the probability of having this ground state solution. I mean the optimal solution. So you can see here that in the end, here in 200, 300, something like that, the quantum annealing start converging to to the optimal solution a bit faster. So you can see here the probability of having that simulate annealing in optimal solution is around 0.9, something like that. So we will go right now to our main thing, so about how we can work with the quantum annealer. So there's famous company called D-Wave company, and this D-Wave company is the only company that work in a quantum annealing direction. Not only, but it's the most company that really put a huge effort in producing good quantum annealer. And right now they have 5,000 qubits and more, about 30,000 connectors. And to understand how we can interact with quantum annealer, we need to create objective function, Ising model or QEGYPT, quadratic and constant binary optimization problems, and we should understand how we can embed this problem in graphs, because DWF quantum annealer has topology. So it's this topology make change every 2 or 3 years. Right now it's Picasso's, and they will release soon Zephyr topology. So quantum annealing in D-Wave, as we if you seen in the beginning of the presentation, we put the quantum annealing equation, in general one. So right now we will talk about D-Wave. D-Wave has flux qubit, which is artificial qubits. They create these qubits, and the equation here is I will explain it, but not necessary right now for to understand how we can use it. So we have this deltas for energy gap. HI is local flux bias for qubit, and we have the current in the qubit loop. This is IP here, and we have the external flux on qubit, and mutual induce this here, and a coupling between qubit I and G. So Ising model and the QEGYPT are same. It can you can convert from Ising model to QEGYPT easily. It's just from mapping binary variables like xi here, 0, 1, just to spin, or vice versa. So usually, it's because people who are right now making algorithms, it's more convenient for them to work with QEGYPT, not with Ising model. So we generally like just take this Ising model and just change it to QEGYPT. It's pretty easy. So, and here is the interesting thing about Cubo. Cubo, it's universal framework to solve a big set of combinatorial optimization problems. Even old car problems, you can use it. You can format it as a Cubo and solve it. But the problem of Cubo, it's MB hard problem. So MB hard problem for classical computers is very hard, and it will take a lot of time. So the idea why is Cubo very interesting for all companies, for even for GetBase, for Quantum, and for every company, because it's Cubo, because it's Ising. So it's the first way to see if we can use quantum to see some advantage and reward. So it's the first thing that we can that has the potential to show that quantum advantage is solving Cubo. And you know, like about supermassive, you know, like there are two supermassive from Google, and one by DOF. I mean, it was like very like maybe 1 month or 2 months, but they did it before, but the paper get accepted like 2 months ago. So what is the thing about this supermassive? The last supermassive from Google, it's good, but the whole problem is not real world application. It's just like random circuit sampling, and this is a random circuit sampling. It utilizes the nature of a quantum, so it's not a good reference to compare between a quantum and the classical. So for that, like even like when they have this supermasses, like it's not a big thing. But about D-Wave supermassive, it was in material simulation, okay, and it was very interesting that they utilize like very big GPU, and they prove that it will take like 100,000 years to get the solution. But even like in this real world application, it utilize the quantum annealing properties. So still like we don't have this real world applications that can enhance industry. But still, there is a way is to use something called hybrid quantum computing. What it means hybrid is hybrid. It means quantum classical. So we have like a way maybe to split problems and embed it on QPUs and try to utilize this to find some speed up like just like 1.2 1.3, and after that merge all the solution using CPUs. So this hybrid quantum computing is right now what a quantum company is using, and this is what we are using as well here in QDeep. So, and Cubo, you can use it for supply chain optimization, traffic flow and route optimization, portfolio management and financial analysis, resource allocation, even machine learning and feature selection, and even robotics. And recently we have a paper that like it's right now it's a preprint. We provide the first demonstration to solve inverse schematics using quantum annealing. So I can like provide the link after the meeting. So here and besides the hybrid quantum computing, there is something called inspired algorithms from quantum annealing, like simulated bifurcation from Toshiba, coherent Ising machine, SimSim simulated coherent Ising machine from QBot. QBot is our competitor right now in Russia. And right now, from our solver, we compete with SimSim, and we provide like better results. And you have digital annealer from Vigisto, it's a Japanese company, and Protes is a probabilistic tensor train sampler. It's developed by IRI institution. IRI institution is a very big institution in Moscow. They use something called tensor train. Tensor train is something come from tensor networks, and tensor networks many the quantum companies right now using tensor networks. So right now, the first real world applications that I will talk about it is traffic flow optimization. So about traffic flow optimization, like 1 hour ago, Nature like report us that the paper got accepted. So like it was like coincidence. So like right now we just like sent like the last they want some editing. So this paper like right now is
Congratulations.
accepted.
This is really great news, Hadi.
Yeah.
Congratulations.
So this paper is why we start with traffic flow optimization, because 5 years ago, Volkswagen company make the first quantum application using quantum annealing in traffic flow. And they use it on China for 418 cars. After that, they use a hybrid quantum annealer to solve it. So in this paper, we use the same technology, D-wave quantum annealing. But what is the difference? I can scroll here and start explaining what we did, because like it can provide more details how we was working on this problem. So first of all, there is something like like people who are working in quantum, they lie usually, and they don't provide the full picture of what is happening. So in Volkswagen project, they said like how they formulate the problem for traffic flow. They said like we have these cars, we have like where they will start, where they will end these cars, and we see the number of cars in each segment. Okay, and we provide for each car 3 routes. So you will have like for each car 3 routes, right? So like each car has 3 routes. So if you have like 418, so the space of the problem is 3 to the power 418. So but if you formulate it to as a cubo, the cubo matrix, it will be 3 times n. So it will be like around 1250, 60, something like that. And what they said in this paper, so they said like the D-wave quantum annealer in that time it was like 1100 or 1200, and they said the D-wave quantum annealer don't have this number of qubits like to 1250, so they will utilize hybrid solver. But what is the like I mean, where is the like I mean, what they hide is if the quantum annealer right now, let's say like 1300, you can't use them to solve cubo with 1300. So I will explain why. Because the wave quantum annealer has this connectivity. So when it was 1200, the maximum cubo, I mean cubo that you can solve is 65. So 65 is around like 20 cars. So the maximum of this hardware is to solve 20 cars. But what they said like something correct, but and not like they don't provide the full picture. So even like the number of cars or I mean the size of matrix is, it was like, let's say like 500. The with quantum annealing can't solve it. Even right now, Cubo more than 180, the wave quantum annealer is not able to solve it. Why? Because you have logical qubits and physical qubits. Logical qubits is in the like Cubo. If you have like 20 by 20 Cubo matrix, it means you need 20 logical qubits. Okay, but there is space to embed these qubits in the topology, and when you are making like more and more, okay, so each qubit will take around 10. I mean, logical qubit, it will take around 10 or 15 physical qubits. So when right now Pegasus, which is a new version, much better, very big, can't solve more than 177. So and for that, like when they said they used hybrid solver, for this reason they were lying, but they had some purpose for industry. So what we did in this paper, so we solve traffic flow for 500 car, but using only the pure quantum process unit. This is 177. But what we did, we utilize the, because like if you think about traffic flow, if you think about it, traffic flow, it's not only connected. I mean, there is localization inside these maps, right? So what we did, we start detecting the mass congested area. Okay. After that, we create we min scale the problem. You know, like we find like where is the max dense problem inside this map. We solve it, and we make more consent on the border. So there is, I mean, when you optimize, it will not take all cars to another region. So it will optimize it. And we detect like sequentially, not in parallel, sequentially, these areas until the solution will converge. So like in usual, like to optimize the map for 500, you need to solve 10 10 problems inside this QBU. And we are not merging the solution, like make it like parallel. After that, we are not merging, like we solve it, we update. So it's like more pure quantum. So what is interesting that we compare our solution, we make more very complex map. Even like this map is very complex. I mean, in their paper just 2 points. In our paper it was like very many points, start points and end points. And we compare our solution with Volkswagen solution, okay? And we add weights, we made a lot of updates. So after that, in solution, we get enhancement for traffic flow around 9 times. So it was like we optimize. If you see here, this left side is traffic congestion before applying our algorithm MTF, many scale traffic flow, and here is after applying. So you see like it's almost like finish. And but here is the worst case scenario, because like traffic flow is real time, so we take it like in worst case. So we are showing the worst case scenario. So in worst case, maybe which will have not happen here, it will just maybe here, and the probability is very 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 small. So we get enhancement between the initial and before and after solving around 65% enhancement, and we get sped up around 10 times sped up. Like in the wave, maybe more. In the wave hybrid solver, it takes 3 seconds, and our solution it take 0.15 seconds, so around 20 times. So this is a first application. So to show like, but how we formulate this problem. So I should explain how we formulate it. We, as we said, like we apply Dijkstra and we make initial solution to see like what is the best route for each car. And after that, when we have the first map, we start making our main map. After that, we put for each car 3 alternative routes. We optimize. After that, like we make it like sequential until the solution will converge. So there are like more like details, but maybe I took more time, so I will try to make some speed up. So the first second
We have,
application is our
sorry,
paper in
Hadi,
ITV Access.
Hadi,
Yeah.
sorry, we'll have to finish in 2 minutes because we are really behind the schedule and
Sorry.
it's really interesting.
I really
Yeah,
tried my best. Like
yes.
sorry.
So
Like
try
I skipped
to,
many
you
theoretical
please,
stuff.
5 minutes.
Sorry, but I really,
Okay.
I skipped many theoretical stuff just to explain. I will try my best right now. So about this paper, what we did, like there is some fundamental machine learning problems. We find them where we can. There is optimization. We formulate SVM, support vector machine, and both algorithms to make it as QBO. After that, we embed it to a quantum annealing, and we apply it on something called admit dataset, which is very important for drug discovery. And the interesting result, because I didn't believe quantum machine learning it will work. I thought this paper will be negative results, but we get enhancement in AUC ROC for QBOST around 4% than the state of art of classical light auto ML. We didn't compare it with SVM and boosting classical because it doesn't make sense. Like we should provide the reader the real good solution. I mean, we can compare it with boosting, classical boosting, and show like better results, but the idea is to show like with very good reference. Last application. Okay, yeah, okay. So I'm almost done. So last application, this paper is about inverse schematic. So inverse schematic, what it means is like like problem in global path planning, and you need to select the angle how the robot will move. So we solve it using quantum annealing. But how we do it? Like we make some selector to select the problem, and we make some linear approximation for this inverse schematic task. After that, we can encode it to QBO. After that, there is something called Ising translation, because the wave quantum annealer accept just flux qubit between -1 and 1, and coupling between -4 and 4. After that, we make embedding, because like you have like different types of embedding, click embedding, general embedding. After that, it go to the wave QBU. After that, it will give you solution. We take the solution, decode it. After that, we find the best angle. So here you can see cubo graph and the real qubits here. So if you see here the white one, okay, here it's 1, 2, 3 qubits. All of these 3 qubits are one variable. So like I'm just like explaining what I was saying before. And this solution is for two linked inverse schematic. So two linked inverse schematic. So you have two angles, and you can see here two yellow points, which is like selecting angle, and you can see corresponding physical qubits in Pegasus topology. Because I should be fast right now. Okay, here we compare simulate annealing, time to solution, and quantum annealing and probabilistic tensor train sampler. And quantum annealing provide around 30 times speed up with simulate annealing and protest solver when we solve a cubo with size 900. So last thing is about new feature properties in the quantum annealing, which is the reverse quantum annealing and fast quantum annealing. Reverse quantum annealing is, like quantum annealing, it's you get initial solution, very bad solution. After that, you get ground state solution. But sometimes quantum annealing can't provide this good solution. So we take the classical solution, we make quantization again. We go with local landscape, and we find better solution. And fast anneal is the last property which they provide the supermassy, and they run anneals for very big problems in less than seven nanosecond in coherent regime. So we're here, and because it's very fast, even the noise can affect the annealing. So for that they get this supermassy. So this is a presentation, and thank you for your attention. So if you have a question, you can like write me, send me an email, or you can ask right now as you want. So yeah, if you have question, I'm ready to answer.
Thank you, Hadi, very much for this very interesting work and for this very interesting presentation. I'm afraid we cannot take questions right now because we are
Yeah,
15 minutes behind schedule.
I,
So this
I,
is
I
the email of Hadi. If you
yeah,
can write it on the chat.
yeah. And
Please, if
just
you
like
have
one
any
announcement,
questions.
announcement. So, I mean, mostly all here from Egypt, I think. So Egypt don't have quantum devices. So we have in QD program for to solve 5,000 cubo free. I mean, you can just like request access. Like it's free for 3,000, but
Do
even
you
like
have you have a quantum computer in Tatarstan
it's a hybrid solver. It's not from Tatarstan, not in Tatarstan, in Russia. Yes, we are right now start
in
working with
Russia? Okay.
Rosatom. Rosatom is nuclear company, so we are right now
Yes, I
have
know that.
collaboration with Rosatom, and we have a quantum annealer, and we have quantum gate based. We have quantum gate based 16 superconductive qubits, and we have a quantum
It's
annealer
very interesting.
around 50 qubits, 50. So we are utilizing these computers in our solvers. So it's but our solvers are hybrid, so quantum and classical, because like it's impossible to run as I explained before. So we are so anyone can solve use I mean just google qdeep.net, so you can get your token. There is SDK. You can start coding. There are some demos, RNA folding, antenna selection, many problems that you can use, and you can start developing your algorithms, your application. Maybe you can run your business utilizing our solvers. And as I told you, like for countries like that don't have quantum devices, we expand our free access for them, but they should request. So we need just more data, like maybe some ID, to make sure that this one is belong for this country, because we don't want to provide this solver for USA or Canada, because we can't do that. Yeah, so
Okay.
so that's all. Yeah.
Okay, okay.
Okay.
Thank you, Adi, very much for your presentation and for your offer. So this is the email of Hadi. I believe many of the Egyptian students will start sending you emails asking for your support to use these
Yes,
quantum
yes, yes.
devices.
I
Thank
participate
you
for this
again.
thing. I just want to participate, like just to even I contact you before, like I contact you before to tell you guys to start utilizing our solver, because like this access is uh, to make some equalization somehow. So yeah,
Okay. Thank you, Hadi. Thank you
yeah.
very much for your presentation.
Mm.
Maybe we can arrange another meeting with Hadi to explain more how can he use students, interested student can use his tool.